The last few questions, titrations of weak acids and bases with buffers, and understanding the predominant species in different solutions naturally leads to question 13 about buffers. So buffers are either solutions we make intentionally or through a titration that have an acid with the conjugate base. And because they have both of those, they're able to resist changes of pHs. So we have to be able to think about what solution could be a buffer, what does it mean to buffer, and what are the reactions that are happening when something is buffering. So on A, it's focusing on what are good buffers. In all of these, it is the same concept. Do I have either a weak acid or base? And do I have a salt that includes the conjugate of that? So yes, in one, HF is weak, F minus is a part of NaF. That is a buffer in the traditional sense. Here in two, we have a weak acid, we have a weak base. There would be some ability to buffer. That would be a little bit trickier, but kind of in our introductory AP Chem sense, we wouldn't normally think of that as a buffer, and we probably wouldn't get that as a question just because that's not the way that we establish a buffer. We need some of this, the conjugate base from HF to be able to do that equilibrium. And we need some of the conjugate acid from this to do that equilibrium. So we'll say no on that. And then you can come back and revisit that and think about the more complex equilibrium and think about how it would be able to do that, but what would it do and what would the pH be at a totally different time. 3 is another one in the traditional sense. Yes, we're good to go. NH3 is our most common weak base. NH4 plus is its conjugate acid. We are good to go. And right here, HCl and NaOH, acid and base, awesome, but we wouldn't have a buffer. Those two would just react with one another. They would neutralize each other and not be able to neutralize anything else. So anything strong can't do it. And we'll establish on some of the problems the exact why in terms of a reaction to practice that idea. On B, it asks about a water, I was going to say solution, but some pure water and what happens when we add sodium hydroxide to it. But then differently, what happens when we add that to a buffer. So when we put a base, in this case, sodium hydroxide into water, it just ionizes. It makes sodium, it makes hydroxide ion. Obviously, there's still the water there. So if we show the water on the reactant side, we have to show it on the product side so that it's balanced. We have made a whole bunch of hydroxide ion. So that makes the OH plus go way up. That makes the H plus or OH minus go way up, the H plus go way down, and our pH has changed. That does significantly change. But in a buffer, we would think about that we have something there that can neutralize our strong base. The part of the buffer that reacts with the base is the acid part. The part of the buffer that would react with HCl or another acid would be the base part. So I don't need to include the fact that I've got sodium nitrite in this reaction because it's the, excuse me, the nitrous acid that is reacting, but both are there. So the sodium hydroxide reacts with the nitrous acid. With a double replacement there, we make water, we make sodium nitrite. So it doesn't make hydrogen ion, it doesn't make hydroxide ion. The sodium hydroxide isn't just ionizing. So that doesn't increase H plus or OH minus, our pH barely changes. In terms of a net ionic, which is much more likely what you'd see and maybe even have to write, the hydroxide ion from this reacts with the HNO2. And even though that's an acid, we draw it all together because it's weak. Well, this is a base, so it accepts the hydrogen ion, so we've made the water molecule, and now we've made some nitrite. That nitrite is a weak base. It can change the pH slightly, but not nearly as much as the hydroxide did. So we have buffered any change of pH. And that'll keep happening until I run out of my weak acid. So eventually we'll get beyond that. We will exceed the buffer capacity and we'll see those terms. But initially, those first few drops barely change the pH. So if this acid and base combo can do this, why can't it if it's strong? And that's something just good to think about the definition of strong one more time. So I've got an acid, Cl minus, that's its conjugate base. This looks a lot like HF and F minus. Why does that do it, but this doesn't? So it's not good enough to just memorize, well, strong can't and weak can. We have to think about what that means. HCl is a strong acid. It can neutralize as many bases as it wants. Great job. If we get them in the right ratio, we'll end with a pH of 7, probably, depending on the strength of the base. The problem is that Cl minus. In terms of a textbook definition, yeah, Cl minus is a conjugate base. But it is super, 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 super weak as a base. It can't neutralize any acids. So awesome, HCl can ionize, that happens, but we write it as a one-way, meaning it can't come backwards. So that Cl will not accept a hydrogen ion to turn back into HCl. So this is kind of the opposite of it, but that Cl minus will not act as a base. It won't neutralize anything. We can neutralize plenty of stuff with the HCl, but the Cl minus from the NaCl is unable to. It's one way, it's not equilibrium. It is so weak in terms of its basic properties that it cannot neutralize.